I'm a teacher Ulimboka Nsujuga Masami. Welcome to Ulimboka Physics. We have a question from Tai, book 3, the concept of light. We have a combinations of concave mirror and the glass slab, and the object placed 21 centimeter in front of concave mirror, and the glass slab is placed at least 1 centimeter from the pole of the concave mirror. The glass slab has a thickness of 3 centimeter and refractive index of 1.5. Okay. Below is diagrammatic representations of the whole of scenario. Let's assume that this is our concave mirror and this is our pole. Let us assume that for better view, this is our principal focus and this is our center of curvature. That's the assumptions, but it's not real that center of curvature is here in this sphere, because center of curvature is required or supposed to be at this point F. But for a better view, let us assume this is principal focus and this is the glass slab that placed the 1 centimeter from P. Okay, we have a 2 rays, red one that is moving parallel from the bottoms and from the bottom and from the top or to the glass slab and to the pole of the mirror. We know from the ray diagrams rules, this is must be reflected back, and also this must be reflected back. Now our incident ray is this yellow one that's from the bottom of this image and incident at point N, and where it's refracted towards point M. This is angle of refraction and this is incidence angle. This is our normal, this is incidence angle. This incidence angle is equal to this angle. This is our opposite angles, and because this opposite angle and after this is refracted rays, and in a second phase there is a refractions, because it undergo first refractions at the first phase of this glass slab and second phase of this glass slab, and this is refracted angle, the refracted rays at the point M, and we know we extended backward this is final refracted ray, so that it will meet this in normal rays NQ at this point that we name it I1, that is image 1 will be obtained here. And also we continue the extensions of this refracted rays up to this up to a principal axis where it meets the lines and form an image 2 here. You know, this is extended, hence the image 2 is visual image that is standing upright as this object. Okay, now the distance BI2 is x, and hence we will have a complete parallelogram BI2 and NI1. This is a complete parallelogram that formed as a result of this refracted rays and this incident ray. Okay, this is a distance Q to I1. This is just a distance H, and this is apparent depth, and a displacement N to I1. This is displacement X, which is one side of this parallelograms, and this side of these parallelograms is simply the same as this one, and also this sides, the longest side of the parallelograms also are the same for I2 to I1 and N to B, but B also short side BI2 is the same as NI1. How? This incidence angle here, this is 100 line, and this is 100 degrees minus theta, because also this one is opposite angle is also incidence angle, and also it is corresponding to this angle here. That's what's also incidence angle theta, and also this incidence angle theta here is opposite to this angle, hence this angle is theta too. But this angle theta is z angle, hence this angle theta is alternate to this angle theta also at image 2 here. Hence this angle is the same as this one, and because this line is 100 degrees, this other side is 100 degrees minus theta. Okay, because this also line is like a transversal line as this one, this angle is the same as this one, because these two angles are alternate angle through this transversal incidence line. Hence this theta, this angle is the same as this angle here, and this angle of this one side of parallelogram is the same as this angle in other side of parallelograms. Hence this parallelogram has equal sides, and therefore the distance displacement x at the inside the glass slab is the same as displacement x at the image 2 with from the object O, and this will be the same regardless of the position of this glass slab. Whenever you take this glass slab along the principal axis, the distance x will not change. Therefore, from this parallelogram also, the distance x from the object to the final image also will not change. Therefore, this displacement x is independent of the position along the principal axis of this concave mirror. Okay, let us do some mathematics so that we can show how we get this displacement x. From Snell laws, as we know, we have sine theta for the incidence and r for refractions. Then we use two triangles, this one and this one, and also MNO, M, also NQ, these triangles, and this triangle for image triangle, and these triangles. Then after using these triangles, we know that will give us the refracted and the incident with common MQ. Okay, then common MQ is cancelled out. Then we substitute this signed letters as this is apparent depth, and this is refractive index of the glass. This is the thickness. Thickness is a distance NQ. Okay, then we know that the refractive index of the glass is equal to real depth, which is thickness T, divided by apparent depth, which is a distance H. Okay, in order to get a value of x, we must take this thickness T and minus from, and take this H and minus from thickness T. Then we remain with distance displacement x, as you can see here. Then from our equations, we make the subject apparent depth H. Then we substitute this H into this H, so that we will get the value of x, which is free from the apparent depth H. Okay, then the final formula will be as you can see here below. Therefore, this value x is independent of any radius curvature or the focal length here, and therefore when it is just depend on thickness of the glass slab and refractive index of the glass slab or of the given material. Therefore, the displacement x is equal to 1.0 centimeter. But from a mirror formula, whenever we use a positive sign conventions, now because it's concave mirror, f will be always positive, object will be always positive. Now our object here is object distance r dash, because it is our visual object, that is image 2. Okay, and it is displaced distance x from the original one. Therefore, the final object distance will be u, the initial object distance, minus x, as you can see here. Therefore, it is equal to 20. From the mirror formula, we will arrive into the final distance of image as 6.67 centimeter. Thanks for watching. Please like, share, comment. Don't forget to subscribe for more.